Hello everyone and welcome back. In this episode I'm going to introduce spatial grids and how we can use them to improve our performance significantly. So first of all, what are spatial grids? If you're coming from game development or if you did any development for games or something like this, computer graphics, anything like this, then you probably already know what spatial grids are. For all the others, we are basically dividing our world in cells, okay, in uniform cells. The width and the height of a cell is equal. There are also other um, optimizations like KD trees, quad trees, and so on. But we are using the most simple one, and this is spatial grids with a uniform size of height and width. So we're dividing our world. Why do we do that? Imagine we have a shape, again a very simple rectangle with which has its bounding box, its blue bounding box, this rectangle here, and it's going around, and then we have other objects. Now you can already see this big rectangle here, this bounding box or this object, is not colliding with other objects with which has a bounding box. In our current simulation, we are checking every object, or let's say every bounding box from every object with every other bounding box from every other object. Okay, and we can avoid that by just checking every cells for multiple objects, like in this case. Here we have a cell which has two objects in it. These bounding boxes are colliding, and therefore this cell will have two objects, this rectangle here and this rectangle there. And now we can just go and look into this cell here, take the objects, and then we can compare for collision. And that's it. For example, in this case here, these cells will have a object 2, but there's just one inside. And when there are just one, we can skip the collision check. Okay, there will be no collision. And that's the optimization. We are not doing our everyone versus everyone check anymore. We are now checking the cells if they have an object, if they have more than one objects, and then we're gonna check these objects against each other. This is our optimization we're gonna implement in the next couple of episodes. All right, so our object with our bounding box. To implement that, we need to do some things. First, we need to somehow calculate the index. Every cell has an index, okay? Starting from the top, goes down and to the right, like this. The left top cell has the index of 0, 0. Then the next one is 1, 0. The next one is 2, 0. The next one is 3, 0, and so on. Same for the y. If you go down, the x value stays 0, y value increases. Also, these cells can have different height and the width. But I'm going to show you how we can do that. Okay, yeah, as I said, we every cell has a width and a height, and in this case, it depends on you. You can say, okay, I want that my cells will have a width and a height of, let's say, 10 or 50 or whatever. It depends on you, and depending on the width and the height, or in general the cell size, you can optimize your simulation further. For example, if you have rectangles which have only the same width and the same height, then you can optimize your cell width and height to this size for your objects. Then you can get even more performance out of that. All right, so let's check how we can map our bounding box. I removed the rectangle from the bounding box now, our original shape. We are just looking at the bounding box because we only need our bounding box for this. Okay, so first cells have a width and a height of 100, all right? And then we have our bounding box. We calculated the top left, the top right, the bottom right, and the bottom left in the last couple of episodes. Our top left has a coordinate of 650 and 350 pixels in this case, in our case. If you doing a other kind of simulation, you usually use a other unit like meters, but for simplicity reasons, we are going to use pixels. Then we have our top right position in pixels. I tried that the coordinates are sorry, kind of right, because this is 90 on the edge on this cell, all right? So every cell has a width of 100. If we count, this will be 100, 200, 300, 400, 600, 700, yeah, 650, that's here, 700, 800, 900, and then 1090, okay? The same for the Y. I think that's pretty obvious how this is working. Okay, so how can we map something into an index of 1 and whatever? I mean, a cell index. So let me show you this. If we have a point, in this case, look at this small stick here, let's say. Okay, and this stick right now has a position of 50. Okay, our width of we are all yeah. By the way, we are only checking now for the x-axis. Okay, that's the exact same thing for y, but I'm only checking for the x-axis now. So this line has the position of 50, and we have a width of 100. A cell has a width of 100. So we are going to divide the position of this stick by the width of the cell. And this is 0.5, all right? And then we're gonna do a little trick. We are parsing this number to an integer. And an integer can't have a number after the comma. All right, so it's going to be 0. Or you can just simply round it down. You can parse it to an int or you can round it down. It's gonna work both. If we go a little bit to the right, let's say we have 99 at the really edge, divided by 100, it will give us 0.99. We're gonna pass it again, it's going to be 0 again. The same with when we round down to a integer number. Really important, it must be an integer number. Then we're going to the next cell. Now we have a position of 110. We're going to divide it by 100. We get 1.1. This we can again parse it. We get, parse to integer or round down. We get 1. Again, 290 divided by 100. We get 2.9. This will be 2. The next one, of course, will be 3, 4, and 5. And now I calculated the x positions for our points. So in the last slide, we are only looking for the x coordinate, all right? We have here 650, 1090, 650, 1090. And we're both dividing by 100. So here we get 6.5, this will be 6. This one, 10,090 divided by 100, this will be 10. And the same for the bottom ones. We need to do the same for the y values. So let's see what's going to be that. That's going to be 2. Of course, this one, this will be 250, I guess. I think it was 250. No, 350. I think that's wrong. I think I made a small mistake here. That must be 250. Sorry for this. And this is probably 695. So I made a little mistake there. But anyways, this will be 6 and 2. This will be 0, 1, 2, 3, 4, 5, 6. This is also wrong. I made a mistake again with the calculation. This must be 695. This also 695. Sorry for this. Okay, and then we have our index. All right. Cool. Now let's check again for the collision part. As I said, every cell has a list, and in every cell we're gonna save the object. In this case, we have our bounding box B. Our bounding box B will be saved in these lists for these cells, and also we have our bounding box A, and we're gonna save it in this one. And in the collision here, we're not doing a collision check, we're just saving every shape into the list, and we're just pushing another item if it's colliding, or if the object is mapping into this cell. We're not doing a collision check, we're just check if a bounding box is mapped into a cell, then we're gonna add this object in it. Then we have two objects in here. All right. Yeah, that's our index calculation. One thing to note: we have our two-dimensional index. We know now, if I go back, we know now the coordinate where we put it, but we can do a performance trick for this too. And that's the trick is we're gonna use one-dimensional lists. So we are converting this two-dimensional grid into a one-dimensional list, and we can do that using a formula, and this is this formula. We're gonna use the x-coordinate for a index, for the x component, and the y coordinate for a y component of a cell index, and we're going to multiply it by the cell count in the x direction. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm not going to count this one. Normally you would count this one, but that's just some yeah, I didn't prepare that this will be another cell for this formula, so I took 12. Just imagine this is our end for the world. There is no other cell anymore there. So we're going to use 12. And now an example, we want to convert a two-dimensional index. We calculated. We can use any two-dimensional index we have. We can use the two-dimensional index for the bounding box, or anything else, and then we can convert this index into a one-dimensional index. And in this case, we're going to use the index 3.31. And if we count now, well, if you look at the formula, you get 15. 15 will be our one-dimensional index where we need to put our shape, for example, in. And if we want to count that, we can actually see that this is right. So if we start here, the first index starts with 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's right. We have the right index here. And now we can have a one-dimensional array of cells. We can map our bounding box depending on the index of the bounding box to that list. So we are going to calculate this index here to a one-dimensional index, and we put we put this index right here into the list. So, well, we're not gonna put that index, but we're gonna put the shape which is inside the bounding box into that list. All right. Technically we can also use the index of the rigid body. You know, we're using an array to represent our rigid bodies, and every item of the array has an index, and you could also use this index, and this will be also a little bit more performance effective. Or you can get a bit more performance out of that too, but it's going to be a little bit more complicated. If you want to do that, of course you can do that. Just try, and yeah. One note more that, well, we have our bounding box, and here you can see we have the index, okay? And we need to map all cells from the touching the bounding box. And we need to put the shape into all of these cells. What we're going to do in the next couple of episodes, we will iterate through all of these index. We're going to use a two-dimensional, we're going to use a nested for loop from index 6 to 10. Then we're going to use another for loop, which we're going to use to loop from 2 to 7 to y, to map this shape into every of these rectangle. Okay, from the for loop we get the index again, we calculate or we convert the index to a one-dimensional index, then we have the index where we're going to put the shape in. This will be these cells here. Yeah, and that's it, what we're going to do. I hope it's not too complicated. I think when I'm gonna start coding that, it should be a little bit more clearer. If not, just watch the video again, or you can also use, of course, some other resources to if you have troubles to understand that. No worries. I had the exact same thing when I started doing this. And one last thing now. This technique, mapping a point into a index, into a cell, will be also really, really useful for future tutorials, especially when I go about fluid simulations, because there we're gonna need that. Yeah, you just have to know what we're doing there. And I'm also explaining that there again. But if you know what I mean, what this is working, then you have a big advantage for my future tutorials. All right, I think I can go now to code and optimize our physics engine. Then see you there. Have a nice day, and yeah, bye bye.